14th of February 1943. Dawn breaks gray over Espiritu Santo. Commander Henry Eccles stands on the coral shore watching a destroyer limp into the anchorage, her hull torn open below the water line. She is the fourth ship this week. He is the supply officer for the South Pacific Fleet, and the numbers in his logbook no longer add up. The destroyer needs 3 weeks in a proper dry dock. The nearest facility is Pearl Harbor, 4,000 miles east. The ship cannot make that journey. Without her, the fleet loses one more gun platform for the push north through the Solomons. Eccles counts the damaged vessels anchored in the bay. 11 ships wait for repair. More arrive each day. The Japanese submarines and coral reefs do not rest. Eccles is 41 years old. He graduated from the Naval Academy in 1922 and spent 2 decades learning how supplies move across oceans. He knows that wars are won by the side that keeps its ships moving. Right now, his side is losing that race. The fleet advances faster than the repair system can follow. Ships pile up in rear anchorages while the fighting moves north. He needs a solution that does not exist. He walks back to his headquarters tent and spreads maps across the plywood table. Espiritu Santo is a volcanic island in the New Hebrides, 800 miles southeast of Guadalcanal. It has no harbor, no dry dock, no infrastructure. The Navy chose it because it is beyond range of Japanese bombers. Now it serves as the main supply base for the Solomon Islands campaign. Eccles must keep the fleet operational from this remote coral atoll with tools designed for permanent harbors. The traditional answer is a floating dry dock. These massive steel structures can lift a ship out of water for hull repairs. But they take months to build, require tugboats to move, and cannot survive typhoons. The South Pacific has typhoons every few weeks. Eccles needs something different, something that can arrive quickly, survive storms, and work without the support systems of a major base. He remembers a concept from before the war. The Navy experimented with sectional dry docks, structures built from standardized modules that bolt together. The idea was to create repair facilities that could be shipped in pieces and assembled on site. The program was small and underfunded. Most officers dismissed it as impractical. Eccles requests the files. The files arrive on 19th of February. Eccles reads through the technical drawings and test reports. The Advanced Base Sectional Dock, designated ABSD, consists of steel pontoon sections, each 10 feet wide and 7 feet deep. The sections connect with heavy bolts and rubber gaskets. A complete dry dock requires between 7 and 10 sections, depending on the size of ship. Each section weighs 30 tons and fits in a standard cargo hold. The concept is sound, but the execution is untested. The Navy built one prototype in 1941 and used it briefly in Iceland. The war started before full trials were complete. No one knows if the sections can survive Pacific storms or if crews can assemble them without specialized training. Eccles calculates the risk. If the ABSD fails, he wastes cargo space and time. If it works, he gains mobile repair capacity that can follow the fleet north. He writes a request to the Bureau of Ships in Washington. He needs ABSD sections shipped immediately to Espiritu Santo. He needs technical manuals, assembly tools, and at least one experienced supervisor. He sends the message on 22nd of February and waits. The fleet does not wait. 2 more destroyers arrive with damage. A cruiser reports a cracked propeller shaft. The anchorage fills with broken ships. The reply comes on 2nd of March. The Bureau approves his request. They will ship ABSD-1, a 7-section dock capable of lifting destroyers and light cruisers. The sections will arrive in 3 cargo vessels over the next month. A civilian engineer named Robert Furman will accompany the shipment. He helped design the prototype. Eccles has 6 weeks to prepare a site and train a crew. He chooses a location on the western side of the island where the coral shelf drops into deep water. The site offers protection from prevailing winds and enough depth for the dock to submerge. Seabees, the Navy construction battalions, begin clearing the area. They blast coral heads, drive mooring anchors into the seabed, and build a small pier for supplies. The work goes slowly. Coral is harder than concrete. Eccles assembles his crew. He needs men who can read technical drawings, operate pumps and winches, and work underwater. The Navy has few trained drydock workers in the South Pacific. Most are back in Pearl Harbor or the West Coast. He takes what he can find: a dozen shipfitters from damaged vessels, a salvage team from a sunken transport, and 20 Seabees with welding experience. None have worked on sectional docks. They will learn as they build. The first cargo ship arrives on 8th of April. Eccles watches cranes lift the steel sections from the hold. Each piece is painted gray and marked with assembly numbers. The sections look smaller than he expected, almost fragile. He wonders if they can hold a 1,000-ton destroyer. Robert Furman climbs down from the ship. He is a thin man in his 50s with oil-stained coveralls and a leather tool bag. He does not salute. Eccles does not care about protocol. He cares about results. Furman spreads the assembly drawings on the pier. The process is straightforward in theory. Float the sections into position, connect them end to end, pump out the water to create buoyancy, then add the end walls and pumping equipment. In practice, every step requires precision. The sections must align within half an inch or the gaskets will leak. The bolts must be torqued to exact specifications or the joints will fail under load. Furman estimates 4 days for assembly if everything goes well. Eccles gives him 3. The crew begins on 9th of April. They use small boats to tow the first section into position between the mooring anchors. The section floats low in the water, its deck barely above the surface. 2 divers go down to guide the alignment. The water is murky with coral sediment. They work by touch, feeling for the bolt holes drilled into the flanges. The first connection takes 6 hours. Furman says that is acceptable. They will get faster. By 11th of April, they have 3 sections connected. The structure begins to look like a dock. The crew learns the rhythm of the work: position, align, bolt, seal, test. Each joint requires 48 bolts and 2 rubber gaskets. The bolts must be tightened in sequence to distribute stress evenly. One mistake can crack a gasket and flood the entire section. The men work in shifts, 12 hours on and 12 off. There is no time for rest. On 12th of April, a storm moves through. The wind reaches 50 knots and the sea builds to 12-foot swells. Eccles orders the crew ashore. The partially assembled dock strains against its moorings. The sections flex and twist, but the connections hold. When the storm passes, the crew goes back out. One gasket has leaked and a section is half flooded. They pump it out and replace the gasket. Furman says the dock survived its first test. Eccles wants to test it with a ship. The remaining sections arrive on 15th of April. The crew works faster now. They complete the assembly in 2 more days. The finished dock is 200 feet long and 50 feet wide. It floats in 40 feet of water, held in place by 8 heavy anchors. Pumps and generators sit on a barge alongside. The dock looks crude compared to the permanent facilities at Pearl Harbor, but Eccles does not need beauty. He needs function. The test comes on 18th of April. A destroyer with a damaged bow arrives at dawn. Her captain is skeptical. He has never seen a sectional dock and does not trust it to hold his ship. Eccles explains the process. The destroyer will enter the dock while it is submerged. Pumps will remove water from the sections, causing them to rise and lift the ship clear of the water. The crew will then have access to the hull for repairs. The captain agrees to try. Furman supervises the flooding. Valves open and seawater pours into the sections. The dock sinks slowly, its deck disappearing beneath the surface. When the water inside matches the water outside, the dock floats neutrally at a depth of 20 feet. The destroyer moves forward carefully, guided by small boats. She positions herself over the submerged dock, her keel centered on the wooden blocks laid out on the deck. Furman signals the pumps. The pumps are diesel-powered and loud. They pull water from the sections at a rate of 5,000 gallons per minute. As the water level drops, the dock begins to rise. The destroyer rises with it. Her hull emerges from the water inch by inch, revealing the torn plates below the waterline. The crew watches in silence. The dock holds. The ship settles onto the blocks with a slight shudder. She is fully supported, clear of the water, ready for repair. The test succeeds. The repair takes 70 hours. Shipfitters cut away the damaged plates and weld new ones in place. Divers inspect the propellers and rudder. The work happens around the clock under floodlights. Eccles watches from the shore. He calculates the time saved. In a permanent dry dock, this repair would take a week. Here, it takes 3 days. The difference is significant. 3 days means the ship returns to the fleet 4 days sooner. 4 days means she is available for the next operation. The math favors the ABSD. The destroyer leaves on 21st of April. Her captain is no longer skeptical. He reports the dock to his squadron commander. Word spreads through the fleet. More damaged ships arrive at Espiritu Santo. Eccles keeps the dock running continuously. A cruiser with a bent propeller shaft. A destroyer with collision damage. A transport with a cracked hull. The crews learn to work faster. Assembly time drops. Repair time drops. The dock becomes a production line, but problems emerge. The dock sections are not identical. Small manufacturing variations mean that some connections fit tightly while others require shimming. Gaskets wear out and leak. Pumps break down in the salt water. Eccles realizes that the ABSD is not a finished product. It is a prototype that must be improved in the field. He begins documenting every failure and every fix. He sends reports to Washington with recommendations for design changes. The most serious problem is typhoon survival. The dock can handle moderate storms, but a direct hit from a typhoon will destroy it. Eccles needs a way to protect the structure. He cannot move it to sheltered water because there is no sheltered water deep enough. He considers sinking it in place, but that takes too long. He needs a faster solution. Furman suggests a compromise. Instead of sinking the entire dock, they can flood selected sections to lower its profile. A partially submerged dock presents less surface area to the wind. The remaining buoyancy keeps it from sinking completely. The crew can then pump it out and resume operations after the storm passes. Eccles approves the plan. They practice the procedure twice before the next typhoon arrives. The typhoon hits on 3rd of May. Winds reach 90 knots. Waves break over the island. Eccles orders the dock flooded to half depth. The crew secures all equipment and evacuates to shore. The storm lasts 18 hours. When it passes, the dock is still there, battered but intact. 2 sections have minor leaks. 1 mooring anchor has dragged. The crew makes repairs in a day. The dock is operational again on 5th of May. Eccles adds the typhoon procedure to the operations manual. By mid-May, the ABSD has repaired 23 ships. The average repair time is now 68 hours. Eccles tracks the statistics carefully. Each ship repaired at Espiritu Santo is a ship that does not have to sail to Pearl Harbor. The round trip to Hawaii takes 3 weeks. The ABSD saves 3 weeks per ship. Over 23 ships, that is more than a year of operational time returned to the fleet. The numbers justify the investment. The success draws attention. Admiral William Halsey, commander of the South Pacific Fleet, visits Espiritu Santo on 19th of May. He inspects the dock and talks to the crew. He asks Eccles how many more docks he can build. Eccles says he can build as many as the Bureau ships him sections for. Halsey says he wants 4 more, positioned at forward bases as the fleet advances north. Eccles begins planning the logistics. The challenge is training. Each dock requires a crew of 30 men who understand the assembly process, the pumping systems, and the repair procedures. Eccles has 1 trained crew. He needs 5. He cannot pull experienced men from other duties. He must train new crews from scratch. He sets up a school at Espiritu Santo. Furman teaches the technical details. The experienced crew demonstrates the procedures. Each new crew assembles and operates the dock under supervision before deploying to a forward base. The first new crew trains in June. They are a mixed group. Shipfitters, Seabees, and salvage divers. Some have never worked on ships before the war. They learn quickly because the alternative is sending damaged ships back to Hawaii. Eccles emphasizes speed and standardization. Every crew must follow the same procedures. Every dock must use the same parts. Standardization allows crews to rotate between docks and allows spare parts to fit any section. It is the key to scaling the system. The second ABSD arrives in July. Eccles sends it to Chalagi, a small island near Guadalcanal. The new crew assembles it in 5 days, faster than the first dock. They begin repairs immediately. A destroyer with torpedo damage. A minesweeper with a cracked keel. The Chalagi dock operates independently, proving that the system can work without Eccles or Furman on site. The crews communicate by radio, sharing solutions to problems. The knowledge spreads. Eccles refines the design based on field reports. He requests stronger gaskets that resist salt water corrosion. He requests backup pumps that can run on different fuel types. He requests lighter sections that are easier to handle. The Bureau of Ships incorporates some changes immediately. Others require months of testing. Eccles does not wait. He improvises solutions with available materials. Seabees fabricate replacement parts from salvaged steel. Divers develop new techniques for underwater repairs. The system evolves. By September 1943, 5 ABSDs operate across the South Pacific: Espiritu Santo, Chilagi, Purvis Bay, Noumea, and F8. Each dock repairs an average of 3 ships per week. The fleet advances north through the Solomon Islands with fewer delays. Damaged ships return to action in days instead of weeks. The Japanese cannot match this repair capacity. Their ships must return to Truk or Japan for major repairs, a journey that takes weeks and exposes them to submarine attack. Many never return. Eccles sees the strategic impact in the casualty reports. The U.S. Navy loses ships to combat but returns them to service quickly. The Japanese lose ships permanently. The balance shifts. By late 1943, the U.S. has more operational destroyers in the South Pacific than at the start of the year despite losses. The Japanese have fewer. The ABSDs are not the only factor, but they contribute significantly. Eccles calculates that the docks add the equivalent of 15 destroyers to the fleet without building new ships. The work takes a toll. Eccles sleeps 4 hours a night. He coordinates supply shipments, manages crew rotations, and solves problems that arise at 5 different locations. Equipment breaks constantly. Sections crack under stress. Pumps fail. Gaskets leak. Each failure requires a solution, and Eccles must provide it. He loses weight. His hands shake from exhaustion. He does not stop. In October, the Bureau of Ships orders him back to Washington. They want him to oversee the production of 20 more ABSDs for the Central Pacific Campaign. Eccles resists. He believes his place is in the field where he can see the problems and fix them. The Bureau insists. They need his experience to train the next generation of supply officers. Eccles agrees reluctantly. He leaves Espiritu Santo on 14th of October 1943. Furman stays to run the docks. In Washington, Eccles writes the official manual for ABSD operations. He includes every lesson learned in the South Pacific: assembly procedures, typhoon protocols, repair techniques, crew training standards. The manual is 200 pages long. It becomes the foundation for all future advanced base operations. The Navy prints 5,000 copies and distributes them to every supply officer in the Pacific. Eccles also testifies before Congress about the importance of mobile logistics. He explains that modern naval warfare requires repair capacity that can move with the fleet. Fixed bases are vulnerable to attack and too far from the fighting. Mobile bases built from standardized sections can be positioned anywhere and provide the same capability as permanent facilities. Congress approves funding for 50 more ABSDs. The program expands beyond anyone's initial expectations. By the end of 1943, ABSD repair times average 72 hours per ship. The original goal was 1 week. The crews exceed it through practice and refinement. They develop shortcuts that do not compromise safety. They learn which repairs can happen simultaneously and which must be sequential. They train new crew members while working, passing on knowledge in real time. The system becomes self-sustaining. The impact extends beyond repair speed. The ABSDs change how the Navy plans operations. Commanders know that damaged ships can return quickly, so they accept higher risks. They push deeper into enemy territory because they have mobile repair capacity following behind. The fleet becomes more aggressive. The advance accelerates. Islands that would have taken months to secure fall in weeks because the Navy maintains constant pressure. The Japanese notice. Intelligence reports from captured documents show that Japanese commanders are confused by the American repair capacity. They damage U.S. ships in combat and expect them to withdraw. Instead, the ships return within days. The Japanese conclude that the Americans have far more ships than intelligence estimates suggest. They do not realize that the same ships are being repaired and returned to battle repeatedly. The ABSDs create a force multiplier that the Japanese cannot counter. Eccles tracks the program from Washington. By mid-1944, 30 ABSDs operate across the Pacific. They repair over 2,000 ships in 18 months. The average repair time is now 60 hours. Some crews achieve repairs in 48 hours for minor damage. The docks survive typhoons, air raids, and equipment failures. They operate continuously with minimal support from rear bases. They prove that mobile logistics can match or exceed fixed facilities. The success validates Eccles' original calculation. He took a risk on an untested system because the alternative was losing the war of attrition. The Japanese had shorter supply lines and could concentrate their forces. The U.S. had longer supply lines and dispersed forces. The only way to overcome that disadvantage was to make the supply system mobile and efficient. The ABSDs did that. They turned remote atolls into shipyards and kept the fleet moving north. After the war, Eccles writes a book about naval logistics. He argues that logistics is not a support function but a combat function. The side that moves supplies faster and repairs equipment faster wins battles. Technology matters less than the ability to sustain operations. The ABSD program proves this principle. The docks were not technologically advanced. They were simple steel sections bolted together. But they were in the right place at the right time, operated by trained crews who understood their importance. The book becomes required reading at the Naval War College. Eccles teaches there for 10 years, training the officers who will plan the Navy's logistics for the Cold War. He emphasizes standardization, modularity, and forward positioning. These principles shape how the Navy builds bases and deploys equipment for the next 50 years. The ABSD program is the foundation. Eccles retires in 1952 with the rank of Rear Admiral. He is 60 years old. He spends his retirement writing and consulting on logistics problems. He advises the Navy on the construction of floating bases for the Korean War. He helps design the supply system for the nuclear submarine fleet. He remains active until his death in 1986 at the age of 84. The ABSDs continue operating long after the war. Some serve in Korea and Vietnam. Others become permanent fixtures at overseas bases. The last ABSD is decommissioned in 1995. 52 years after the first one arrived at Espiritu Santo. Over that time, the docks repair tens of thousands of ships. They save countless lives by returning damaged vessels to service before they can sink. They prove that logistics innovation can change the outcome of wars. The site at Espiritu Santo is abandoned after the war. The coral grows back over the mooring anchors. The pier collapses into the water. No marker indicates what happened there, but the impact remains. Every modern naval base uses modular construction techniques derived from the ABSD program. Every rapid deployment force relies on equipment that can be shipped in sections and assembled on site. The principles that Eccles developed in 1943 are now standard practice. Historians debate the importance of the ABSD program. Some argue that it was a minor innovation in a war won by industrial production and technological superiority. Others argue that it was essential to maintaining the operational tempo that defeated Japan. The truth is somewhere between. The ABSDs did not win the war alone, but they prevented the U.S. from losing the war of attrition. They kept damaged ships in the fight when those ships would otherwise have been lost. In a war decided by narrow margins, that contribution was significant. Eccles himself never claimed credit for winning the war. He saw his role as solving a specific problem: how to repair ships faster than the enemy could damage them. He approached it as an engineering challenge, not a strategic masterstroke. He tested a solution, refined it based on results, and scaled it when it worked. The success came from persistence and attention to detail, not genius. That is the lesson he taught his students and the lesson that survives him. The equation he faced in February 1943 was simple but impossible. The fleet needed repairs faster than the system could provide them. Traditional methods could not close the gap. He needed a new method. The ABSD was that method. It arrived in crates, assembled in days, and repaired ships under fire without a permanent harbor. It turned remote atolls into mobile shipyards. It reduced repair times from weeks to 72 hours. It kept the fleet moving north while the enemy waited for parts that never came. That is what remains. Not the steel sections, which rusted away decades ago. Not the crews, most of whom are gone. But the idea that logistics can be fast, mobile, and decisive. The idea that supply officers can shape battles as much as combat commanders. The idea that innovation comes from solving immediate problems with available tools. Eccles proved those ideas at Espiritu Santo. The proof changed how navies operate. The change endures.